guys, today we are going to discuss on the topic of Tyler and Maclaurin series. These were the series in the following form: C sub n times x to the n from 0 to infinity. We mentioned that the sum of a power series can be represented by a function with terms involving each power of x all the way to the infinity. But we may want to know something about all of these coefficients. Now that we understand differentiation, we are ready to expand our understanding of this kind of series. So let's talk about this now. Say now we're looking at this power expansion. The series C sub n times the quantity x minus a raised to the n power. We can describe this function, but we may want to solve for these coefficients. It actually won't be as tricky as you think, given the difference x minus a in each of these terms. If we find f of a, all of these binomials become 0 and therefore all these terms becomes equals to 0 except for the first coefficient here, which is c0. So f of a equals c0. With the first coefficient down, how do we get this is where the differentiation comes into play. Let's say we take the derivative of this function. c0 will go away since the derivative of any constant is 0. And for the second term, x minus a will go away, leaving c1. To be clear, if we were to distribute before taking the derivative, we would get c1 x minus a. And since c1a is just a number, that will go away and c1x will become c1. For the other terms, we will use the chain rule. Starting with this one, the 2 comes down here, leaving an exponent of 1. And then we multiply by the derivative of what's inside, which will just be 1. So we are left with 2c 2 times equals to quantity x minus a. The second part of the chain rule will always be 1 for the rest of this term. So we can just do the part with the exponent. 3 comes down here and the exponent becomes 2. 4 comes down here and the exponent becomes 3. Now with this expression, which represents the first derivative of function, if we plug in a, all of these terms will disappear, just like when we plugged in a into the original function. The only thing left is c1. So f prime of m, or the derivative of evaluated at a, equals c1. Let's go back to the expression for the first derivative and take the derivative again. c1 goes away and this term becomes 2c2. Then we have 2 times 3 for the 6 times quantity of x minus a. This next coefficient becomes 12 and so forth. Again plugging in a for x will isolate the 2c2 term. So f double prime of a equals 2c2 or c2 equals f double prime of a over 2. By now, we might see a pattern, right? Taking the third derivative and plugging in, a will give us f triple prime of a equals 6 3 or c3 f triple prime of a over 6, which can also be expressed as 3 factorial. In putting a into the fourth derivative of f will give us 24c4, leaving that c4 equals to the fourth derivative of f over 4 factorial. We can therefore set up an expression to find the nth coefficient of the series. C sub n equals to n derivative of f evaluated at m divided by n factorial. This works for all the terms, even the first, if we understand the zeroth derivative of a function is simply the function itself, and the 0 factorial equals 1. So to summarize, for the function given by the sum of c sub n times the quantity x minus a to the n power, where the absolute value of x minus a is less than the radius of convergence. For the series, the coefficient of the function are given by this formula. If we then generate a new function of the same form, but substitute this formula in c for sub n, such that the terms in this series looks like this, we have just generated the Taylor series of the function f at m, which is also described as f about m, or f centered at a. So, a Taylor series is a type of power series, but with the coefficients defined like so. Now we understand what a Taylor series is. Now let's define what a special case is. For the same type of function, but where a equals to 0, this binomial becomes simply x to the n, and everywhere we're plugging in a, we simply plug in 0. So we get f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, and so forth. This is a special kind of Taylor series called a Maclaurin series. This is a Taylor series where the expansion is about point x equals 0. So we should definitely be aware of this definition for the Taylor series and Maclaurin series because we're going to apply these expansions to specific functions. Take for example e to the e power x. Let's find the Maclaurin series that represents the function f of x equals to the x. That will be the end derivative of e to the x evaluated at 0 over n factorial times x to the n. Well, what do we know about e to the x? The derivative of e power x is e power x. So no matter what derivative we're looking at, we just have e power x. Also, we're plugging in 0 every time, and anything to the 0 power is 1. That means any derivative of this function evaluated 0 will give us 1. So this entire time can just go away, leaving us with x to the n over n factorial. We can therefore quite easily begin writing out the series with x to the 0 over 0 factorial, or simply 1 plus x to the 1 over 1 factorial plus x squared 2 factorial, and so forth. This should look very familiar as we have just derived a form for the e power x utilized earlier in the calculus series. That form is actually the Maclaurin series for the function. Let's make sure we can find the radius of the convergence for this function. That will require the ratio test. We set that up and flip the denominator to get the x to the n plus 1 over n plus 1 factorial times n factorial over the x to the n. After some simplification, we can cancel terms and we get the absolute value of x over n plus 1. As n approaches infinity, this goes to 0. 0 is less than 1. So this series convergence for all values of x and the radiance of convergence is infinite. Taylor series have many applications, but for now it's enough for our discussion. So bye guys.